Hi, everyone, and welcome back to the Regression and Beyond series. In this lab, we're going to focus on path models and mediation. As before, you can find the data in script file linked below, as well as some helpful references if you're interested in some further reading. So, we are going to focus on mediation, but more broadly in the context in path models. And there are several reasons that I present it this way. I'll note a lot throughout the lab, but some to note at the beginning. One, the contemporary approach to testing mediation is essentially a path model. Specifically, this is the product of coefficients approach, and I'll be demonstrating that and talking more about that later. But that's the contemporary approach in contrast to the Barron and Kenny approach, or the three steps causal approach. Another broad reason to talk about mediation in the context of path models is because path models are relevant to structural equation models, which might be a topic of interest to you. And I'll do a basic introductory video and maybe some further detailed videos down the way, but one for sure on a basic introduction in this video series. But for now, focused on the path model part, which is relevant because the typical structural equation model has two components, a measurement model and a structural model. And often that structural model is a path model. So we're focused on the path model part today, but basically everything that we talk about would be relevant and will apply in the context of a structural equation model. So those are just two to initially note off the bat. Otherwise, to get going, we're going to follow steps that we've done before in all the previous labs. So I'm loading the Rio package and then importing the data for this one. It's 500 observations of 4 variables. Then I run the summary real quick. And it looks like they're basically all continuous variables. The model we're going to start out with, relatively straightforward, simple path model. I'll know our X we're treating as our independent or exogenous variable. Then our M1 and M2 are the mediators. Y is going to be our dependent variable. Our first model, we're just going to include X, M1, and Y. So we're going to have M1 mediating the relationship between X and Y, or in other words, X predicts M1 and then M1 predicts Y. So kind of a triangle shape, often depicted that way. And we're going to use this package Lavaan. You can install it here if you don't have it installed. And then we will load it. Lavaan is going to be very useful if you get into latent variable modeling more broadly and you want to use R. So again, another reason to kind of focus on path models. We're not going to focus on that part of it, but it will be relevant later down the line. So one initial thing to note, the commands are very similar to what we've done before. You'll see basically for regression, we've used this tilde. I think you pronounce it. So M1 is regressed on X, Y is regressed on M1. You'll see now we're putting that in quotation marks. And then we basically have two separate parts rather than before we basically had one all together. First, we do our model, and then we actually fit that model to the data in a second step. So this first one, again, you can name it whatever you want. I'm keeping it simple. So path model 1, but broadly, this is our model, right? Then once we have that, you'll see some things pop up here, but basically nothing has happened because we haven't actually estimated the model yet. We just said this is actually what our model is. And now we go to actually fit the model. Again, you can name this whatever you want. And you'll see, again, relevance to when you get into structural equation modeling. We're actually going to use that command. Then we're specifying, yes, this is the model and this is the data. And we'll use that summary function to have a look at it. So before kind of looking at the model estimates, several things to talk about on that output. First, you'll see the estimator is ML. This stands for maximum likelihood. In the previous labs, we have been using ordinary least squares. We could have used maximum likelihood, and many of the things we'll talk about today, like testing mediation, you could actually use with ordinary least squares estimation. But generally, in I think a lot of ways, and some of the more advanced models that we'll get into, the general default is maximum likelihood estimation. So this is one way to introduce it. Without getting into all the ins and outs, conceptually, it's similar to ordinary least squares in that we're trying to minimize the gap between our model and our data. Again, conceptually. The name is different because it says maximum, but we're technically choosing the estimates that kind of maximize the likelihood that our model implied data matches our actual observed data. And the way I like to think about maximum likelihood is like climbing a mountain. If you climb up and up and up, at some point when you get to the peak at the very top, if you took one more step, you'd actually be stepping down. Similarly, maximum likelihood in the way we're going to apply it here is an iterative process. We're going to try out a bunch of different parameters until we hit that peak point, where if we took another step, we'd actually get worse. So it involves, again, multiple steps. It's not an exact solution like ordinary least squares. We try a bunch of things out until we hit that criterion or until we hit that peak. But maximum likelihood is going to come up a lot in future videos. Next thing to note, we have model test user model. Specifically, the test statistic here is a chi-square, and overall, this is a likelihood ratio test. So remember, maximum likelihood I just mentioned, conceptually similar to ordinary least squares, trying to kind of conceptually at least minimize the difference between what our model implies that data and the data that we have observed. And the likelihood ratio is basically a formal test of that. Technically, we call it an exact test. So this is a chi-square statistic, and then we have 1 degree of freedom. The reason we have that 1 degree of freedom is because we're actually excluding a path that we could be including. Specifically, we're not including a relationship between X and Y. Remember, we just said X predicts M1 specifically, and then M1 predicts Y. So there's no relationship. That's why we have 1 degree of freedom. So chi-square, 1 degree of freedom. And again, this chi-square statistic is basically a quantified difference of between model implied data and actually sample observed data. And in this case, it's another one where we generally do not want a statistically significant result. I'll note in kind of reality in practice, I think I've almost always had this be statistically significant. It's not the end of the world, but in this case, it is really nice. Again, it's suggesting that our model is an exact fit to the data. which is a good thing. So when we have at least 1 degree of freedom, we would call this a just identified model. So that means, again, in this case, we could add one thing that we currently are excluding. So there's basically one combination that we're excluding that we could be including. So over identified. Just an identified model, you would have 0 degrees of freedom. So to just illustrate that real quick, we can add in a relationship between X and Y. So first step, you'll see I've just changed the name to JI. So I'm going to do a just identified model. And I just added in the X here. Otherwise, everything else is similar. But if we go up and look to the test statistic, you'll see that it's 0 and it has 0 degrees of freedom. So technically, it's a perfect model. We can't falsify this model. Philosophically, often seen as a bad thing, because at least according to Popper, and kind of sticking with that view, we want kind of useful, simple models that can be falsified. A just identified model is always a perfect fit, so we can't falsify it. So not inherently a bad thing, though. You might have an interesting model that is a just identified model. The classic mediation model generally would include that relationship between X and Y and would be a just identified model. But again, on kind of the other side of it, you can't really test it against the data, and you can't test it against other models. Again, that's called a 0 degrees of freedom. That's called a just identified model. Now let's move towards actually testing the indirect effect, or actually testing mediation. We just have to make some small changes here. So you'll see I added the letter A and B right here to our original path model. These are simply labels. And the reason we're adding labels is because I'm using them down here to define something. This is what this command is doing right here. You could name this whatever you want. Specifically, I'm just calling it the indirect effect to keep things simple. Remember, again, I'm using the product of coefficients approach. So we're literally multiplying 2 coefficients. So I've labeled them A and B, and I'm saying the indirect effect is A times B. So adding labels, otherwise everything else is basically the same. Next part is mostly the same, but you'll see that we're adding in this bootstrapping idea. So why are we doing this? Well, broadly, the source of the reason is that the sampling distribution for the product of coefficients is not normal. So not always, but typically we'll assume when we're doing a hypothesis test, something like the standard normal distribution is the sampling distribution. For example, you might take a coefficient, divide it by a standard error, turn it into a z-score, and compare it to the critical z-score. In this case, that would be inappropriate because the sampling distribution is not normal. Generally, I'll put some references there to read more about that. If you have a really large sample size, it doesn't seem to matter too much. It might be okay. But generally, the common approach is to use bootstrapping. And with bootstrapping, what we're going to do is empirically generate a sampling distribution for hypothesis testing. And bootstrapping, what it does is randomly resamples our data, estimates the model. It's going to multiply those coefficients, then save them, and then do it thousands of times, as many times as we tell it to. And that's how we're actually going to create this distribution. So in this case, you'll see Bootstrap 1000. General recommendation is to use at least 5,000 or more. But for simplicity sake and to keep things relatively short, I'm going to do 1,000. Depending on your computer, it can take a relatively long time if you're going to do a lot. So we're just going to keep it to 1,000. You'll see blue pops up. Otherwise, nothing else happens, but you will see this little stop sign down here. That can commonly show up where R is actually doing things in the background, but nothing is popping up. So that's okay. I like to, you can kind of compare a little bit bootstrapping and maximum likelihood, at least with metaphors. I said maximum likelihood was kind of like climbing a mountain. Bootstrapping is kind of like running on a treadmill until you hit a certain number of miles. You're repeatedly doing something, right, over and over and over again. And then we could do something like, look at your average minute, your distribution of times, running times over that particular length that you ran. So that's what maybe not super helpful, but maybe can be a helpful way of thinking about it. Just repeatedly doing stuff and saving it. So that finished up. Again, on your computer, it might take longer or shorter. So now when we just do the summary, things are basically looking the same. The only difference that pops up is you'll see standard errors are bootstrap standard errors. So they are going to be, or potentially can be, different depending on the scenario. One thing we'll talk about, and I think maybe the next lab or the one after that, when we have violated assumptions, bootstrapping, using bootstrap standard errors is actually one approach to dealing with specific violated assumptions. Or if you have heteroscedasticity, it can be one approach to addressing that. But commonly, indirect effects are reported along with a confidence interval. And remember, we empirically generated that sampling distribution, and we can use it in different ways. We can create a confidence interval in different ways using that distribution. This first one, I'm going to be using the bias corrected. It's a little bit confusing because it says BCA, but as far as I can tell, looking at the documentation, it's the simple bias corrected. So remember I said that the sampling distribution is not normal. The basic ideas of this, it's actually a z-score correction that quantifies the amount of bias, and we just add that as a correction when we're creating the confidence interval. I'll set a paper that talks a little bit more about that one, but that is commonly used. So if we look down here, we want to look at indirect. We see that we get the estimate, and then we get the lower and upper values of the confidence interval. Notably, we can use this parameter estimates command to get all sorts of things. So for example, we can do a different type of confidence interval. Specifically, we could use the percentile approach, and that's just looking at the 95 percentiles, essentially, or 95% of the distribution where that falls. And this is a common alternative in terms of bootstrap confidence intervals for indirect effects. You can also get standardized coefficients and things like R square. So if I just run that real quick, you can see that now we get some more information. For example, the R squareds are popping up right here. We get the indirect effect down here, and then we get the intervals. And then typically, in terms of standardization, you're probably going to want to look at this column, the std dot all. Again, there might be some exceptions, but these are what we call the completely or fully standardized coefficients there. All right, so that's where I'm going to finish things in this video, but in the next video, we'll pick up here right where we left off. Thank you for watching so far, and hope to see you in the next video.